Hello, everybody. Hello.
Hello.
How's everybody doing today? I hope you had a good weekend. Are you guys able to see my screen?
No, but we can see you.
You can see me. Oh, okay. I must have forgotten to share the screen. Okay, here we go. How about now?
Yes.
And how is the audio and the video?
I am.
Just a second. Is that a little bit better? Okay, so you can see the PowerPoint. I'm just going to kind of zoom through to, I think, where we left off. Did anybody have any questions?
For the volume quiz that's due tonight, how many questions are on it?
I don't know, but if you send me an email, once we're done, I will check and I'll let you know. How does that sound?
Okay, thank you.
And I will be posting a test soon also. I'm still working on it. I think this might have been where we left off. And I think we were kind of like in the middle, but I'll go ahead and just start at the beginning. Okay? So it says the row of Pascal's triangle that starts 1, 4 would be useful in finding probabilities for an experiment of tossing 4 coins. Interpret the meaning of each number in the row. So I just started at the beginning. I said if we flip a coin once, we're either going to get heads or tails. And that corresponds to this first row here, where we have a 1 and a 1. And if we flip a coin twice, we can get heads, 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 tails, tails, heads, or tails, tails. So there's one outcome that has both heads. There's 2 outcomes that have one head and one tail. And there's one outcome that has both tails. So that would correspond to this second row here. And if we flip a coin 3 times, there's one outcome that has all heads. There's 3 outcomes that have 2 heads and a tail. There's 3 outcomes that have 2 tails and 1 head. And there's 1 outcome that has all 3 tails. And that corresponds to the third row. So looking at our fourth row, that's going to show us how many different combinations there are with a certain amount of heads and a certain amount of tails. Okay, so there should be 1 way to get all heads, 4 ways to get 1 tail, 6 ways to get 2 tails, 4 ways to get 3 tails, and 1 way to get 4 tails. And there is indeed 1 way to get all heads. And there's 4 different ways to get 1 tail, 6 different ways to get 2 tails, 4 different ways to get 3 tails, and 1 way to get 4 tails. And there will be 16 outcomes total in the sample space. And we just get that by adding up the number of outcomes. So we add the 1 and the 4 and the 6 and the 4 and the 1. And so that gives us the 16 outcomes that are in the sample space. We could just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 also. Part B says to find the probability of getting exactly 1 head and 3 tails. So that's going to be the number of outcomes that have 1 head and 3 tails divided by the number of outcomes in the sample space, and that would be 4 out of 16 or 1/4. Part C says find the probability of at least 1 tail. So one way we could do that is if we get at least 1 tail, that means we have 1 tail or 2 or 3 or 4, and we can use the additive rule. So we do the probability of 1 tail plus the probability of 2 tails plus the probability of 3 tails plus the probability of 4 tails. So we get the number of outcomes with 1 tail out of the sample space plus the number of outcomes with 2 tails out of the sample space plus the number of outcomes with 3 tails out of the number of outcomes in the sample space, plus the number of outcomes with 4 tails out of the number of outcomes in the sample space. Right? And so we get 4/16 plus 6/16 plus 4/16 plus 1/16, and that gives me 15/16. Is that okay so far? I'm going to look at that one again. So remember, the probability of the complement of event A is 1 minus the probability of event A. Okay. Also, if we solved for the probability of event A, we would find the probability of event A is equal to 1 minus the probability of A complement. So, for example, if this was 1/4 and this was 3/4, 1/4 equals 1 minus 3/4. Or 3/4 equals 1 minus 1/4. So if event A is the event of getting at least 1 tail, the complement means you don't get at least 1 tail. In other words, you get 4 heads. So the probability of event A, the probability of getting at least 1 tail, is 1 minus the probability of the complement. So 1 minus the probability of getting 4 heads. So we can do 1 minus the number of outcomes that have 4 heads out of the number of outcomes in the sample space. That's 1 minus 1/16, which is 15/16. So 2 different ways to do that problem, right? We end up with 15/16 both times. And then part D says, should you bet in favor of getting exactly 2 heads, or should you bet against it? The probability that you get exactly 2 heads is the number of outcomes with 2 heads out of the number of outcomes in the sample space. That's 6/16. And the probability of not getting exactly 2 heads, that's 1 minus the probability of getting exactly 2 heads. So here I'm using the complement rule. It's 1 minus 6/16. That gives me 10/16. Okay? And 10/16 is bigger than 6/16. So you are more likely to not get 2 heads since it has a bigger probability. So you should bet against getting 2 heads. Anybody have any questions? Next, we're going to look at number 14. It says if each of the 10 digits, 0 through 9, is chosen at random, how many ways can you choose the following numbers? First, we have a 2-digit code number, and you're allowed to repeat digits. So the number of ways of choosing 2 digits. Here we're going to use the fundamental counting principle that we saw last week. It's the number of ways to choose the first digit times the number of ways to choose the second digit. Okay, and we have 10 different options in each space. So we multiply 10 times 10, and that gives me 100. So there's 100 different ways that we could choose that. Part B is a 3-digit identification card number where you're not allowed to use a 0 as the first digit. So again, we're going to use that fundamental counting principle. The number of ways to choose the 3 digits is the number of ways to choose the first digit times the number of ways to choose the second digit times the number of ways to choose the third digit. So since we're not allowed to use 0 as the first digit, there's only 9 choices for the first digit. And there's 10 choices for the second digit and 10 choices for the third digit. So we come up with 900 different ways. Does that make sense so far? Part C is asking about a 4-digit bicycle lock number. And this time, you're not allowed to use any digit twice. So if the first digit is a 9, you're not allowed to use a 9 as the second digit or the third digit or the fourth digit. The number of ways to choose the 4 digits is the number of ways to choose the first digit times the number of ways to choose the second digit times the number of ways to choose the third digit times the number of ways to choose the fourth digit. So we have 10 different digits we can choose from for my first digit. And whatever I use as my first digit, I'm not allowed to use that as the second digit. So there's only 9 choices for the second digit. And whatever digit was used in the first or the second place, you can't use again for the third place. So now there's only 8 different digits that you could use in the third spot. And then whatever you used in the first 3 spots, you're not allowed to use in the fourth spot. So there's only 7 different digits you could use for the fourth spot. And then I just used my calculator and multiplied 10 times 9 times 8 times 7, and that gave me 5,040. So that's the number of ways to choose the 4-digit lock number. And the next one, I think it might be D, but that's okay. A 5-digit zip code number with the first digit not 0. But this time we are allowed to repeat. The number of ways to choose the 5 digits, the number of ways to choose the first digit, times the number of ways to choose the second digit, times the number of ways to choose the third digit, times the number of ways to choose the fourth digit, times the number of ways to choose the 5th digit. And the only restriction is that the first digit can't be 0. So there's only 9 choices for the first digit. And then there's 10 choices for the second digit, and also for the third, and also for the fourth, and also for the 5th. And that gives you 90,000 different possibilities. Any questions on any of that? Next is number 15. It says if 8 horses are entered in a race and 3 finishing places are considered, how many finishing orders are possible? We have 8 horses, and we're really interested in knowing who comes in first, who comes in second, and who comes in third. And after that, we don't care. So the number of ways for the top 3 places to happen is the number of choices for the first place times the number of choices for the second place times the number of choices for the third place. And there's 8 horses, so there's 8 choices for who comes in first. Whoever came in first isn't a possibility for second place, so then there's only 7 choices for second place. And then whoever came in first and second can't come in third, so then there's only 6 possibilities for the third place. And 8 times 7 times 6 gives us 336. If the top 3 horses are lucky 1, lucky 2, and lucky 3, in how many possible orders can they finish? So now we know that those are the top 3 horses. So the number of ways for the top 3 places to happen, it's the number of choices for first place times the number of choices for second times the number of choices for third. And now we only have 3 choices for who comes in first. It's either lucky 1 or lucky 2 or lucky 3. And then once we've chosen the horse to come in first, there's only 2 choices left now for second place. And then once we've picked someone for first place and picked someone for second place, there's only 1 choice left for third place. And that gives us 6 different possibilities. And we could even just list out those 6 different ones. What is the probability that these 3 horses are the top finishers in the race? So we want to know what's the probability that the top 3 are lucky 1, lucky 2, and lucky 3. So that will be the number of outcomes with those 3 horses in the top 3 places out of the number of outcomes in the sample space. And we just figured out that there were 6 different outcomes with those 3 horses in the top 3 places, and there were 336 outcomes altogether in the sample space. Anybody have any questions so far? Okay, so that was number 15. Oh, and then I reduced that, and that reduced, I divided the top and the bottom by 6, and that gave me 1 out of 56. So number 16 says 3 children are born to a family. Draw a tree diagram to represent the possible order of boys and girls. So the first branching says the first child's either a boy or a girl. And if the first child's a boy, the second child's either a boy or a girl. And then the third child, again, is either a boy or a girl. So if we follow the top branches, that's having 3 boys. Or we could have a boy first and then a boy and then a girl. So boy, boy, girl. We could have a boy and then a girl and then a boy. So boy, girl, boy. Or boy, girl, girl, right here, and so on and so forth. Part B says, how many of the outcomes involve all girls, 2 girls and 1 boy, 1 girl and 2 boys, or no girls at all? So there's 1 outcome that has all girls, girl, girl, girl. There are 3 outcomes that have 2 girls and a boy. So you could have girl, girl, boy, girl, boy, girl, or boy, girl, girl. There's 3 outcomes there. And then there's 3 outcomes that have 1 girl and 2 boys, girl, boy, 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 girl, girl, or boy, boy, girl. And then there's only 1 outcome that has no girls. And by the way, these are the numbers from Pascal's triangle again. So this is the 3rd row of Pascal's triangle. How do these results relate to Pascal's triangle? They're the numbers. That should really say from the 3rd row. Not sure why it says the 6th row. It should be the 3rd row. Okay, number 17. In shooting at a target 3 times, on each shot, you either hit or miss. And we're going to assume that those results are equally likely. The 1, 3, 3 row of Pascal's triangle can be used to find the probabilities of hits and misses. Okay, so there's 1 way to get 3 hits. You get hit, hit, hit. There will be 3 ways to get 2 hits. So you could do hit, hit, miss, hit, miss, hit, or miss, hit, hit. There will be 3. And there will be 3 ways to get 1 hit. Could be hit, miss, 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 hit, miss, or miss, miss, hit. And then it'll be one way to get no hits, miss, miss, miss. There's 8 total. We add 1 plus 3 plus 3 plus 1, we get 8. And then the probability, we just take 1 out of 8, 3 out of 8, 3 out of 8, and 1 out of 8. And then part A, it says use Pascal's triangle to fill in the entries in the following table for shooting 4 times. All right, so we're going to use Pascal's triangle. So here's our triangle. We're going to use the 4th row again. There's one way to get all 4 hits. There'll be 4 ways to get 3 hits, 6 ways to get 2 hits, 4 ways to get 1 hit, and 1 way to get 0 hits. If we add up the numbers here, we get 16. And so the probability of getting 4 hits will be 1 out of 16. The probability of getting 3 hits will be 4 out of 16. The probability of getting 2 hits will be 6 out of 16. The probability of getting 1 hit will be 4 out of 16. And the probability of getting 0 hits is 1 out of 16. Okay, so use Pascal's triangle to fill in the entries. Which is more likely that in 3 shots, you'll have 3 hits, so you'll only take 3 shots and all 3 of them are hits, or that in 4 shots, you'll end up with 3 hits and 1 miss? So which one of those is more likely to happen? So here are the 2 charts that we've already had. We're again trying to figure out which one's more likely that in 3 shots, you end up with 3 hits, or that in 4 shots, you have 3 hits and a miss. So the probability of getting 3 hits when you have 3 shots, that's 1/8, which is the same as 2/16. Or the probability that when you have 4 shots, you get 3 hits and 1 miss, that's 4/16. You're more likely, this is a bigger number, so that means it's more likely to happen. You're more likely to get 3 hits and 1 miss with 4 shots than to get 3 hits with 3 shots, right? So basically when you have that 4th shot, you're giving yourself a chance to miss 1 shot, but still end up with 3 hits total. Any questions on anything so far? Number 18 says the Los Angeles Lakers and the Portland Trail Blazers are going to play a best 2 out of 3 series. So that means that out of 3 games, whoever wins 2 games will be the winner. And the tree shows the possible outcomes. So if LA wins the first game and the second game, they don't bother playing a 3rd game because they know that LA will win. On the other hand, if LA wins the first one and then Portland, if LA wins the 3rd one, then LA wins. Or if Portland wins the 3rd one, Portland wins. And if Portland wins the first 2, then they don't bother playing the 3rd game because they know that the winner will be Portland. If the teams are evenly matched, then each one has a 1/2 chance of winning any game. So we're going to label the branches of the tree with the appropriate probabilities. And that looks like this. So every branch has a 1/2 probability. All right, did all that. Part B, find the probability that Los Angeles wins the series in 2 straight games. So that would be LA wins and then LA wins. And find the probability that Portland wins the series after losing the first game. So that means LA wins the first game and then Portland wins the second and Portland wins the 3rd. So the probability that LA wins in 2 straight games, that's the probability that LA wins the first game times the probability that LA wins the second game. So that'll be 1/2 times 1/2. Here we have a 1/2 and here we have a 1/2. and that gives us 1/4. The probability that LA wins the first one, and then Portland wins the second, and Portland wins the third, that's the probability that LA wins the first game, times the probability that Portland wins the second game, times the probability that Portland wins the third game. So we're multiplying 1/2 times 1/2 times 1/2, and that gives me 1/8. Find the following probabilities. The first one is that LA wins when 3 games are played. So the way that could happen is that LA wins the first one, and then Portland wins, and then LA wins. Or that Portland wins the first one, and then LA wins, and then LA wins. All right? So using the additive property, that's the probability that we have LA, Portland, LA, plus the probability that we have Portland, LA, LA. And remember, all of the branches are 1/2, so we're going to multiply 1/2 times 1/2 times 1/2. That's the LA, Portland, LA. Or for the second one, we have 1/2 times 1/2 times 1/2. All right, so that gives me 1/8 plus 1/8, which is equal to 2/8 or 1/4. Okay, the next one we want to look at is the probability that Portland wins the series. So if Portland wins the series, that means they have to win 2 out of 3. So it could be LA wins and then Portland, or Portland wins and then LA wins and then Portland wins, or Portland just wins the first 2 games and they don't bother to play the third game. And we can use the additive property. So we do the probability that LA, Portland, plus the probability that Portland wins the first, LA wins, and then Portland, plus the probability that Portland wins the first 2 games. So we do LA, Portland. So that's LA, Portland. That's 1/2 times 1/2 times 1/2. That's right here. And then we do Portland, LA, Portland. So that's 1/2 times 1/2 times 1/2. That's right here. And then the other possibility is that Portland wins and then Portland wins. So that's just 1/2 times 1/2. So here we get an 1/8, and here we get an 1/8, and here we get a 4th. So we have 1/8 plus 1/8 plus a 4th. That makes 2/8 plus a 4th, which is 1/4 plus 1/4. And that gives me 2/4, which is a 1/2. Is that all okay so far? And then the third one, the series requires 3 games to decide a winner. So there's 4 different ways that can happen. We can have LA, Portland, LA. We can have LA, Portland. We could have Portland, LA, LA. Or we could do Portland, LA, Portland. Okay, and we can use the additive property to split those up. And now remember, each branch is a 1/2. So we'll do 1/2 times 1/2 times 1/2. LA. LA, Portland, LA, Portland. That's a 1/2 times a 1/2 times a 1/2. And then for the other ones, we also have 1/2 times 1/2 times 1/2, and 1/2 times 1/2 times 1/2. And those all end up giving us 1/8. So we have 1/8 plus 1/8 plus 1/8 plus 1/8. And that gives me 4/8 or 1/2. You also could have done this one using the complement. You could have said, well, if we're trying to find the probability that it requires 3 games, the complement of that would be it only requires 2 games. So we could have done 1 minus the probability that it only requires 2 games. Any questions so far? Number 19, it's the same sort of situation. It says Team A and Team B are playing a best 3 out of 5 series to determine a champion. Team A is the stronger team with an estimated probability of 2/3 of winning any game. So Team A can win the series by winning 3 straight games. And that path of the tree would look like this. Team A wins, Team A wins, Team A wins. Next, we want to label the branches with the probabilities and find the probability that this occurs. So remember, there's a 2/3 probability that Team A wins. So we're going to label a branch that ends at A with 2/3, and we want to find that probability. So the probability that A wins and A wins and A wins would be 2/3 times 2/3 times 2/3, and that gives me 8/27. Team A can win the series in 4 games by losing 1 game and winning 3 games. This could occur as B-A-A-A, A-B-A-A, or A-A-B-A. And they say, well, why not this one? Why not A-A-A-B? Well, because if Team A wins 3, they don't bother to play the other games. So we wouldn't do this. That would be what we had on the previous slide. And then it says, compare the probabilities of the following paths. So the probability of B and then A and then A and then A. Remember, there's a 2/3 chance that A wins. That means there's a 1/3 chance that B wins. So we have a 1/3 chance that B wins times 2/3 times 2/3 times 2/3. That gives us 8 out of 81. And the next one, A wins, there's a 2/3 chance of that. And then B wins, there's a 1/3 chance of that. And then A wins, that's 2/3, and A wins, that's also 2/3. So this also comes out to 8 out of 81, okay? So that means if we have 3 A's and a B, the probability of that will always be 8 out of 81. What do we observe? And what's the probability that Team A wins the series in 4 games? So what we observe is that the probabilities are always the same, because we're always going to have 3 factors of 2/3 and 1 factor of 1/3, and that'll always make 8 out of 81. The probability that Team A wins the series in 4 games, well, there's 3 different ways that can happen. It can be B-A-A-A, A-B-A-A, or A-A-B-B, and we can use the additive property to split that up. And we know we're going to get 8 out of 81 plus 8 out of 81 plus 8 out of 81, and that'll give me 24 out of 81, and that reduces down to 8/27. Is that okay so far? Says the series could go to 5 games. Team A could win in this case by winning 3 games and losing 2 games. They do have to win the last game though, because if they won 3 games and it wasn't the last game, then the series would be over, because as soon as somebody wins 3 games, they don't bother to play the last games. So first we're going to list how could that happen. So it could be 2 B's and then 3 A's, B-A-B-A-A, B-A-A, B-A, A-B-B-A-A, A-B-A-B-A, or A-A-B-B-A. We just need to make sure there's 3 A's and that the last one is an A. What is the probability of each of those ways? So the probability of a B and a B, well, that would be 1/3 times 1/3, and then 3 A's, that's 2/3 times 2/3 times 2/3, that makes 8 out of 243. And all of these options will have that same probability, because there's always 2 B's, so there'll always be 2 factors of 1/3, and there's always 3 A's, so there'll always be 3 factors of 2/3. And it doesn't matter what order you multiply these numbers in, you'll always get 8 out of 243. So what is the probability of Team A winning the series in 5 games? So we have the probability of any one of these options, and there are 6 of those options. So we're going to add 828 out of 243 to itself 6 times. We can do that by just multiplying 6 times that fraction, and we get 48 out of 243, which reduces down to 16/81. Is that okay so far? What is the probability that Team A will be the winner of the series? And what's the probability that Team B is the winner? The probability that Team A wins is the probability that they win in 3 games or 4 games or 5 games. And we've seen each one of those probabilities already. So we split it up. It's the probability that Team A wins with 3 games, plus the probability they win with 4 games, plus the probability that they win with 5 games. We saw the probability that they win in 3 games was 8 out of 27. The probability that they win in 4 games was also 8 out of 27. And the probability that they win in 5 games we just saw was 16 out of 81. 8 27ths plus 8 27ths gives me 16 27ths. Then I get my common denominator, so I have 48 81st plus 16 81st, and that makes 64 81st. So that's the probability that Team A wins. The probability that Team B wins, I'm going to use the complement rule. That's going to be 1 minus the probability that Team A wins. We just saw that the probability that Team A wins was 64 81st. So we're going to take 81 81st minus 64 81st, and that gives me 17 81st. Any questions about anything so far? Okay, we're going to take a quick look at number 20. It says, complete the tree diagram to show the possible ways of answering a true-false test with 3 questions. So the first question you either answer as true or false. Second question you answer as true or false. And the third question you answer as true or false. So you might say true on all of them, or you might say true on the first 2 and then false on the next one. So here are all of the different possibilities. All right, so you could do true on all of them, true, true, false, true, false, true, true, false, 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 true, true, etc. How many possible outcomes are there? Well, we can just count 1, 2, 3, 4, 5, 6, 7, 8. There's 8 possible outcomes. How many give the correct answers? All right, so the teacher, if they have an answer key, they know that the first one is either true or false, and the second one is either true or false, and the third one's either true or false. There's only one correct answer for all of them. Does that make sense? So what's the probability of guessing all the correct answers? It's going to be the number of outcomes that has all correct answers out of the total number of outcomes. So the probability of guessing all 3 questions correct is 1 out of 8. Sound okay? Okay. Number 21 says, your sock drawer contains 2 blue socks, 2 brown socks, and 2 black socks. Without looking, you pull out 2 socks. Draw a probability tree diagram. We're going to use the letter E for blue, N for brown, and K for black. All right. So remember, at the beginning, there's 6 socks. 2 are blue. So you have a 2 out of 6, or 1/3 chance of drawing out a blue. Same thing for brown, and then same thing for black. Once you've drawn out a sock, there's only 5 socks left. If you drew out a blue one the first time, there's only 1 blue sock left. So you have a 1/5 chance of drawing out a blue. There are still 2 brown, so there's a 2/5 probability of drawing a brown, and a 2/5 probability of drawing a black, because 2 of the 5 socks are black. If you drew out a brown one the first time, there's still only 5 left, but 2 of them are blue. So you have a 2/5 chance of drawing a blue. There's only 1 brown, so there's a 1/5 chance of drawing a brown. And then there's 2 blacks, so there's a 2/5 chance of drawing a black. And then something very similar if the first one you drew out was black. The first time